Okay, let's go full screen. Okay, even I have to teach even to an empty room, but thankfully it's not empty today. But okay, so we're gonna take a break from supervised learning for now. We've been beating that to death for the past 3/4 of the course. So we're gonna venture on to something new, which is unsupervised learning, something you haven't seen before. If you've taken image processing, you might have heard of k-means clustering. I don't know if you have, but I'm still gonna cover it anyway. But it's one of the most popular unsupervised learning algorithms. It's very simple to implement, and it's very easy to understand, which I'll cover next. And then we'll get on to an interesting topic, which is called dimensionality reduction. So basically, if you have a data set that's millions of features, maybe there might be some desire to be able to visualize that data set, because you can't visualize anything beyond 3 dimensions. So dimensionality reduction takes your data set and reduces it down to fewer set of features. You can either visualize it, or you can maybe perhaps perform some sort of data compression, whatever you want. But I'm going to cover dimensionality reduction, which it requires a method called principal components analysis, and you use singular value decomposition to compute the PCA. So I'll cover those next. Just a shameless plug. I don't know if you know about the faculty course survey. They used to do it on paper, but now it's completely online. It's digital, which is nice, save the trees and all that. So basically what you do is for every course that you take at Ryerson, you optionally have the right to fill out a course survey for every course that you take. So it's a course survey that talks about what you liked and what you disliked about the course. It's all multiple choice, there's no full answer, like, did the prof show up on time to his office hours? Did you understand the materials? Simple yes or no questions or true and false. It's totally optional, but if you do fill it out, you get entered into a draw to win a bunch of prizes like an Apple Watch or Apple Swag or whatever, so it's optional, it's totally up to you. Between March 24th and April 4th, so it won't start till Thursday. By all means, please fill that out if you wish. But it basically tells Ryerson how I'm doing in terms of performance. Like if there, and it's also completely anonymous. You don't, there's no identification involved. But it basically tells Ryerson what you liked and what you disliked about the course, what improvements can be made for the next year. I don't know if they'll take that into consideration, but it also allows me to continue teaching because it has feedback associated to it. So if you like how I teach and if you want me to continue teaching for the next year, then by all means, please fill it out. But it's totally up to you. It's just a shameless plug if you wish. It's totally optional. How you fill that out is you go to your Blackboard page, mine.ryerson.ca, and then as soon as you log in, there's a main page. And then in the participate section, there's a link called faculty course survey. So it's not available now. It'll be available on Thursday, and you have 2 weeks to fill it out. So if it's completely optional, I just wanted to put that in. I'll also send an email out just to remind people. Okay, so recall, let's go back to supervised learning. So supervised learning, what was the goal of supervised learning? It was you had a bunch of training examples, and then each example had an expected output and expected label for each training example. And the goal was to create a prediction model that would accurately predict each expected label given the particular training example. So we wanted to build a prediction model that was supervised, or that had expected labels that we wanted to take into account. Okay, so it creates a prediction model to predict or classify, depending on what you're doing, if it's regression or classification, or classify an input, using labeled data. So labeled data is important. Okay, so here's a quick example. Let's say we've got 2 features and the goal is to classify, find a decision boundary, right? Just a quick, because I'm not going to do any numerical stuff, but this is just a quick illustration. So I have a bunch of examples here. This is a nice linearly separable decision boundary, something like this. And the goal is to find a nice decision boundary. So that was the purpose. Okay, and I guess you can call these positive examples and you can call the other ones negative examples, that's fine. And these are negative examples. Okay. And these are 2 features, x1 and x2. Okay. Okay, so your training set, your training examples consists of features and the associated label for those features. So the training set, right, it consists of, you've got one example with an expected label, and then you have the next example with an expected label, and then you have M of them here. There's M possible training examples. And you create a prediction model that will accurately predict the output given a particular input, right? So these guys are your examples, right? And these guys are your labels. labels or expected output. It depends on what task you're doing. Okay, so that's supervised learning in a nutshell. All right, so that's what we've been dealing with so far in the course. This is just for about 3/4 of the course so far. Okay, so now we're going to get onto the topic of unsupervised learning. This one's the more interesting one, especially if you want to get into like the big data movement or the deep learning stuff. Stuff that you deal with in data science or stuff that you see in the industry nowadays. They tend to focus on unsupervised learning because there's a lot of data to deal with, and there's no mechanisms to be able to sift through that data as quickly and as accurately as possible. So unsupervised learning is something that's more popular currently. Okay, so the purpose of unsupervised learning is you have a bunch of data and we actually don't know what any of those labels are. So you've got a bunch of data and the whole point of unsupervised learning is to find some sort of meaning or group the data into particular clusters of points where each cluster has some sort of relation or some sort of similarity between every single point in that cluster. So the whole point is to take data and group them into certain groups. That's the whole point of unsupervised learning. Okay, so in a nutshell, you find structure in data. Okay, so what you're not given any label information, so you're not given any expected outputs or any labels for each training example. You're just given examples by themselves. And the whole point is to be able to find some sort of structure in your data or to take the data and put them into some meaningful groups. And each group should have some similarity between them. Right, so the goal is to place examples into groups. Okay? So that's what it is in a nutshell. All right. So the method to take unlabeled data. So these are just examples with absolutely no label information. We don't know anything about the data except that there is a bunch of features for each example. So the method to take unlabeled data and put them into groups is called a clustering algorithm because each group you can represent as a cluster of points, and each point in that cluster is similar to every other point in this cluster in some way. All right? So the method to take unlabeled data and putting them into groups, or putting into groups, is called a clustering algorithm. Okay? So here's a quick example. So let's say I've got, here's a little example here. So let's say I've got a bunch of features like so. Okay? And there's absolutely no information about it. We just know the data looks like this. So this is just two features, just to be simple. Okay? So we can see here that we can kind of group this data into two clusters of points. So we might consider this as, group 1, and we might consider that as group 2. We can clearly see that there's two clusters of points. So each group is called a cluster by tradition. So you can either call them a group or call them a cluster, doesn't matter, but in most literature they call this group a cluster of points, which is why it's called the clustering algorithm. Okay? So each group is called a cluster. Well, it's called a cluster of points. So each group is not called, but it's a cluster of examples. Let me just clarify, is a cluster of examples. All right? So having some similarity with each other. So every single example in the cluster has some sort of similarity between them. So our job is to figure out what that similarity may be. Okay? So your training set, it consists of absolutely no labels. We don't know anything about it other than the fact that we have data. So you just have x1, x2, up to xm. There's m examples. And we don't know anything. So there's no label information. Okay? There's absolutely no information at all. No label information. So you might be thinking to yourself, what are some example applications of clustering? Why would we want to use clustering to begin with? Well, the main driving force behind clustering is you have such a huge data set that you don't know where to start, and you want to be able to find some structure in that data set. So one example might be perhaps medical imaging, where you take a look at several MRI images and you want to be able to cluster them or group them into similar images which may exhibit similar traits. These MRI images may have some sort of cancerous tumors in them. I know some other MRI images might be clean. So the whole point is to take MRI images and cluster them into different groups, where each group has some similarities between them. Some have cancer, some don't, some don't. So that's one application. Okay, so given medical images, it doesn't have to be MRI. It could be mammograms or anything dealing with medical imaging. MRI or CT or so on. It doesn't have to be just MRI. It could be any image, any kind of image data you want. So given medical image data from different patients, okay, we want to find groups of patients who have similar, similar, I guess, cancers or similar traits between them. And you want to see what characteristics make each of these examples in that particular group similar to each other. Okay? So see what characteristics make them related. The next example is there's a huge uprising or a huge surge in popularity, social media. Very huge for unsupervised learning. So let's say you're on Facebook, or if you're on Twitter, or any social media website, and there's a whole bunch of people that like a similar page or like similar interests. So unsupervised learning will take these people and group them into clusters where each person in this group likes a particular set of pages or has a particular set of interests. And you might want to create a targeted ad or something that will, that'll appeal to this group that like these particular subjects. So, unsupervised learning is actually a nice tactic for, targeted advertising. All right, so group people, who like the same interests or like the same pages. Same interests. And provide targeted advertising. That's one particular example. Or sometimes what they'll do is they'll see what people like and perhaps make their website better to be able to target their website towards that kind of people, those kinds of people. That's a particular example. And last but not least, unsupervised learning is actually heavily used in academics because, for example, you want to be able to perhaps group people into different performance categories. These people got A's and these people got A pluses, and you want to be able to figure out what makes these people so special for them to get these grades. Do they study more? Do they sleep less? Do they drink coffee more? So it's kind of a cool thing to be put into academics. So you can actually figure out how people perform in different grade categories. All right, so academics. Actually used quite a lot. So, group students into different categories. Of performance and examine, why exactly they perform that way. What particular set of features or what similarities between these students in that particular group do they perform the way they do? Yep.
Just a quick question. Why is it, for example, in the academics, this isn't something that can be performed with supervised learning? Because you could use these things like we're talking about,
you could.
Sleep and whatnot, as features?
Yeah, you could do that for sure, but then you can actually do it supervised and unsupervised, but people like to do unsupervised because there's so much data to deal with, and to be able to manually assign labels to each of these students might be manually intensive. So supervised learning could be done if your data set's quite small, if it's manageable, let's say hundreds or thousands. But if you have millions or perhaps billions, then that might be a little unwieldy. So yeah, it depends on the data. So unsupervised learning is very suitable for large data sets, and supervised is used for relatively small ones. But I see your point. So it depends on the size of your data set. So if it's small and manageable, then supervised totally. But if it's really large, then you don't want to sit there and go through a billion records like, okay, this guy is performing well, this guy is not performing well, then that's a little unmanageable, right? Unless you get thousands of peons to do it for you, but I don't think that's.
So the idea of unsupervised this almost automatically?
Yep. So the whole point of unsupervised learning is to find structure in data. So you have a bunch of data with no label information, and the job is to put this data into groups where each group has some similarity with each other, and it's your job to figure out why they're similar that way. Okay? Okay. All right. So those are some really cool applications. Okay, so in this course, I don't know if you've covered this, I don't know for those who are taking image processing or what that, but there's a very popular algorithm which is called the k-means algorithm. So if you haven't covered that yet, no worry, I'm going to cover that. But in this course, we're going to cover a very simple clustering algorithm which is known as the k-means algorithm. It's actually one of the most simplest algorithms in practice, mainly because it's easy to implement and it's very easy to understand. Okay, so in this course, we will study the k-means algorithm. Okay, it's one of the most easiest to understand and simplest to implement. Doesn't require a lot of crazy algebra at all. It's mainly just, looping through a bunch of examples and finding distances and all that. So, we are going to cover another unsupervised learning algorithm later, which is called self-organizing maps, which is basically using neural networks to perform unsupervised learning. I'm going to leave that towards the end because it's a little more complicated, but we will cover another technique, which is called self-organizing maps, which is actually a pretty cool topic. So we will also cover self-organizing maps, or they're called SOMs for short, but not yet. We'll do that later. Okay? Okay, let's get on with k-means. Okay, so with k-means, there's one important warning that you have to know. It's with k-means, unfortunately, you need to know how many clusters you're looking for before you actually do the algorithm. So you have to set a variable saying, I'm looking for 4 clusters of data, or I'm looking for 6 clusters of data. So you have to know how many clusters you're looking for before you start the algorithm. Okay, so this algorithm assumes we know how many clusters we want, or how many clusters we're looking for before we start the algorithm. Okay, so how many clusters we need beforehand. So in Latin, this is what is known as a priori. So it's prior knowledge that you know before you actually do something. So you'll see that in textbooks a lot. If they say that you have a priori knowledge, it means that you have prior knowledge or some knowledge that is available to you before you actually do some sort of experimental process. Okay? So the number of clusters that you want to have is equal to k. That's why it's called k-means, because you're looking for k clusters in your data, and the whole point is to separate this into k groups. That's why it's called k-means, because you have k clusters. All right? So k-means. And the means will actually be very obvious in a little bit when I actually cover what this algorithm does. Okay, so each cluster of examples, so you have examples that are split up into different groups. Each cluster of examples is represented by a single point, which is called the centroid. Right? This centroid is the representative of all of the examples in this particular group. It's what's known as a cluster centroid. All right, so each cluster of examples is represented by what's known as a cluster centroid. Cluster centroid. All right, so it is a representative of every single example in this cluster. So when you choose a particular example in this cluster, the cluster centroid will speak on behalf of that particular example. All right, so it is a representative of all examples inside the cluster. Okay, so it's defined obviously in the same feature space as all the other features in your set. So it's defined in the same feature space as the examples, which makes sense. Okay, so the notation we're going to use is mu, and then 1, mu 2, and then all the way up to mu k. Okay, so there's k centroids, and each centroid is represented by mu because it's, you know, it's actually represented as the mean, but we'll talk about that later. Okay, so here's the algorithm, you know, no fooling. So I'm gonna represent the algorithm, you know, it's gonna, you know, there's a bunch of, you know, pseudocode here, a bunch of steps we're gonna follow, and then obviously it would be nice to actually see this in practice. So I'm gonna show a graphical example after I lay out this algorithm. Okay, so at the very beginning, we're given some training, we're given, you know, M training examples. Okay, and we don't know any label information associated with each training example. So, okay, we have no idea, you know, what the label information is. Also, we need to know the number of clusters as well. I'll talk about, you know, how to choose how many clusters there are towards the end. It's actually an unsolved problem, but I'll give you some insight on how to choose it. Also, I like to drop the convention that there's a bias term. There's no bias term, right? Because you need that in unsupervised learning to calculate the bias in order to create the decision boundary and all that. But we want to find data and put them into groups, so there's no bias term here anymore. Okay? So each example has n features, and there's no bias. So there's no x0 equals 1 and all that stuff. Okay? So there's no bias term. So this x0 equals 1 stuff, we don't need to know that. Okay, so that's what we're given. The first stop is to perform some initialization, as we usually do whenever we, you know, perform some algorithm. Okay? So the first step that you have to do is you have to assume something about the cluster centroid. So you have to randomly initialize them to some points. Either you can randomly initialize them, or what you can do is you can choose a bunch of random points in your examples to serve as the initial centroids or the initial cluster centroids. Okay? So randomly randomly initialize the cluster centroids. So there's k of them. All right, so mu1, mu2, all the way up to uk. And there's different ways you can choose them. So the first method is you can randomly initialize. So you can just give them, you know, pretty much any values you want. There's one method. Or what you can do, which is randomly initialize with random values. Just want to make that clear. Or what you can do, which is actually seen in practice, is to choose k random examples in your data. Okay. Also, you have to make sure that they're unique. I like to point that out. So, you know, sometimes when you randomly choose, there might be a case where it's called selection with replacement, where you might have, choose one example which serves as a initial cluster centroid, and then you might choose the same example, and that's not permitted. So when you randomly choose k centroids, make sure that each point is unique. There's no commonality between the two. Okay, so it's unique. Okay, and this part, this one, part B, where you're choosing random examples, that is what is actually seen in practice. Okay, so this is usually done. Okay, also, so unique, what I mean by that is all centroids are unique. I like to point that out. Okay, so that's their initialization. So you're going to take your k centroids and just initialize them to some random values. So they're defined in the same feature space as, you know, the examples. Okay? Okay, 2. Here we go. So this is the main algorithm. So we're going to repeat until convergence, and I'll talk about how this algorithm converges at the very end. So I just want to lay out the steps here. Okay. So when you repeat, so you choose the initial clusters, you initialize the cluster centroids, and then you repeat 2 steps continuously until the algorithm converges. The first step is what's known as the cluster assignment step. Okay? So what the cluster assignment step means is that what you're going to do is you're going to go through every single training example that you have, and for each training example that you have, what you're going to do is you're going to find the distance from that example to all of the centroids that are defined in your data. And then what you're going to do is that example will belong to the cluster that is the closest to the particular centroid you're looking at. So for example, let's say you've got 4 centroids, and you find the distance between one example to 4 of the other centroids. And you notice that the distance between that example and centroid 3 is the smallest. So what you're going to do is you're going to take that example and give that label 3, which means that this belongs to centroid 3, so this, I'm assigning this to have a label of 3. Okay, then you repeat that for every single example that you have in your training set until you finish all the examples. Okay, so for every training example that you have, okay, so what you're going to do is you're going to, let me move this to the side. I need some room here. Okay, so what you're going to do is you're going to compute what's c, to the power of I, or it's superscript I, which is the index of the cluster centroid closest to the example that you're looking at. Okay, so what this variable says is that it tells you which cluster or which group that this example will be grouped to or will be assigned to. Okay, so C superscript I tells you which which cluster X of I is assigned to. Okay, and the distance that we're going to use here is the Euclidean. So the distance measure used is the Euclidean distance. That's the only one we're going to use in this course. There's other distance measures, and some of them have certain properties like rotation and variance and all that stuff, but we're not going to cover that here. But there's more than one possible kind of distance. Okay. All right. So what I mean here specifically is that this particular label for this cluster gets assigned the label J, where J is, let me see here, what I mean by that is, let's see here. So example X of I is the closest to centroid UJ. Okay, so that's what that means. So what I mean by this is, it belongs to that. Also, what I mean is that it belongs to cluster J, I guess. So we'll put that in. Just want to make that clear. Okay. So when I have a particular label for a particular example, C superscript I, so that's saying the label that is associated with the example I is J, where J is the closest to centroid J, or J will belong, or example I will belong to cluster J. All right? So mathematically, we find J such that you want to figure out the minimum distance from this example to every single one of your centroids. Okay, so that's what we mean. Okay? So whichever centroid gives the smallest distance, okay, to xi, that's what you give that label for that particular example. Okay, so that's the cluster assignment step. Okay, so that's the first step. The second step is to update the centroids, so it's known as the centroid movement step. So update centroids, which is what's known as the movement step. And basically it's like this. So what you're going to do is you're going to take a look at all of the examples that were clustered into each group, and then what you're going to do is you're going to take every example that belongs to cluster 1 and average all the points together to create a new centroid. Then you take a look at all the examples in cluster 2 so far, average all the points, and figure out what the average would be for point number 2, for centroid number 2, then you keep going to the very end. So this is why it's called k-means, because what you're doing is once you figure out where each example maps to a particular group, you find the average of all the features that belong to that group, hence the means, and that is the centroid for the next step. Then you go back and repeat the process, until the centroids don't move anymore, or if the label information from the previous iteration to the next iteration doesn't change. and then you're done. It's a very simple algorithm. Okay, so the update step, what you're doing is you're going to iterate through every single cluster that you have for small k up to large K here. What you're going to do is you're going to update the centroid. So this is what's known as the update step. So what you're going to do is average all examples that belong to cluster K.
Sure.
Yep.
What if, like, when you're randomly choosing the centroids are very similar?
Yes. So that's actually the problem with k-means. Because what will happen is that if you have a bunch of data where the centroids are very similar to each other, it'll actually be quite hard to separate between the two. So what you have to do in practice is you have to randomly do this about 100 times or so, and then choose the configuration that produces the least cost. Which helps. So you're jumping the gun. I'm going to cover that later, but it's good that you're asking that question. But yes, it's actually a common problem with this because if you have a lot of overlapping data, then if you happen to choose two centers that are close to each other, then it's actually quite hard to split them up. So you have to rerun k-means and keep randomly choosing until you produce the configuration that has the lowest cost. But yes, that's a very good question. Okay? Okay, so average all examples that belong to cluster K. Okay? So basically what this is doing is that when you're performing this average, what's happening is that the centroids will move in a better position that will better represent all of those examples in that particular group. All right? So centroids move in a position more suitable to represent the cluster. Okay? So you're finding all that, and then what you're going to do, so how you exactly calculate this is very easy. So let me just write that down. So what you're doing is you are finding the average, and what you're doing is you're summing over every example where that label belongs to this cluster, and then you just, let me see, not mu, so J. Okay? So this here is the number of examples in cluster K. Okay, so what this funny notation says is that what you're going to do is you're going to go over every single example that belongs to cluster J and just sum them all up, sum every single feature up individually, and just find the average. Okay? So this all examples with label K. All right? So let me just give you a concrete example. So example. Okay? Let's say, the label information for example 2 belongs to cluster 2. And let's say number 6 belongs to 2, and 8 and 10 also belong to 2. So what this is saying here is that examples 2, 6, 8, and 10 all belong to the same cluster, which is number 2. Okay? So if you want to figure out what the new centroid is, all you have to do is just add up all these examples that belong to cluster 2. So this becomes 1 over 4, x of 2 plus x of 6, x of 8, and then plus x of 10. Okay? So if you want to actually give, just to give you a numerical example, or not a numerical example, a concrete example. Okay? So, and that's pretty much all you do here. All right? So then you do this, and then let's see. And that's it. All right? So first what you do is you figure out what the assignment is. So what you're doing is you're figuring out which example belongs to which cluster. And then after, what you do is once you figure out what the memberships are, you average all the examples for that particular cluster. So you update the centroids, and then you go back to the beginning and redo that assignment step. So with those new centroids, figure out what the new label information is. And once you find the new label information, average all the points in each cluster and keep repeating until the labels don't change or the clusters don't move by a certain amount. So that's when you finish. Very simple algorithm to implement. Okay, so the convergence. Convergence is when cluster assignments don't change, or we reach a maximum number of iterations. Because you might get to a point, as what you talked about, where you have two centroids that are in data that's overlapping. So sometimes the k-means algorithm will not converge. So you're going to have to stop it after a certain number of iterations. So either when the clusters don't move anymore, or if you reach a certain number of iterations, and that's when you stop. Okay? Or we reach a maximum number of iterations. Oh, yeah. Okay. All right. Let's see here. So this also means that the centroids stop moving. Because, yeah, think about it. Because if the label information doesn't change, then the centroids don't move, because the average from the previous iteration will match the current iteration. So if the centroids don't move, then the label shouldn't change as well. So they both are the same. All right. This also means the centroids don't move. Okay. So the expected output is basically, for each example, you're going to have a label from 1 to k that is assigned for each example, as well as you're going to output the cluster centroids for each cluster that you have. So that's the expected output. All right. So the output would be the label information for each training example that you have, as well as the centroids for each cluster that you have. Okay? All right, so that's the expected output. So that's what we see. Okay. So I'm going to write a little note here, which is pretty interesting. So as I talked about, what we can do is we can take each training example and represent them by the corresponding centroid that is part of that cluster. So you can actually do a data compression where, let's say you've got let's say you're looking for 6 clusters, and what you're doing is when you do this assignment step, what you're doing is you're taking each example and assigning it so that it only belongs to one of the 6 centroids. So you're compressing your data from, from a range of, that's infinitely many down to just between 1 and as many k centroids as you have. So you can actually do some sort of data compression. So we can do a data compression by changing each example to be the centroid of the cluster it belongs to. Okay? So what I mean to say is that if I have some training example, I can transform this so that it's represented by the centroid located at P, where P is the cluster that this example belongs to. Okay? This is actually quite useful, and I'll talk about that in a little bit. Okay. So let me just talk about some advantages and disadvantages, and I'll show you a quick example, and then we can take a break. All right? So advantages. Okay. There's few advantages, but they're quite important. The one thing is that it's a very easy algorithm to understand, and it's very easy to implement. So I guarantee you that once you look at this, you're probably thinking to yourself, yeah, I can write some code for this. It's pretty easy to do, right? So advantages: 1, easy to implement and understand. This is probably one of the most simplest algorithms we've seen in this class. It's just find the assignment, find the centroids, repeat until you're done, right? So easy to implement and understand. Also, if your data tends to be well separated, like you have a bunch of data into different clusters, then this is a very good algorithm to use to be able to separate your data into clusters automatically. All right? So if the data is well separated, let's see here, we can find clusters easily. And the third advantage is that there are many efficient algorithms to do this. So there are many algorithms which is known as finding the closest pairwise distance between 2 points. There are very efficient algorithms to do that. So if you use that and corresponding with k-means, you actually get a very fast algorithm for unsupervised learning. So many efficient algorithms exist to find distances or minimum distances fast. Okay? But unfortunately, this algorithm is fraught with many disadvantages, but you also have to figure out, is this the right, the one question you have to ask yourself is, okay, is this the algorithm for me? So you take a look at the advantages and also the disadvantages, and then you weigh them out, and then maybe you figure, okay, this algorithm is good for me because of, certain reasons. The one disadvantage is that you have to know how many clusters there are beforehand. Are there 2 clusters or are there 4 clusters? You won't know. You have to experiment. So that's one disadvantage we have here. So we need to know how many clusters we want in advance. That's the sucky part. 2. So if you take a look, the core part of this algorithm is that you have to randomly initialize your centroids. So a problem with this is that different random initializations may give you different decompositions of your data. So one random initialization, if your data is non-overlapping, may give you a different cluster or centroid configuration. And then if you randomly initialize it with a bunch of other points, it may give you another centroid or another cluster definition. So there's a way to combat this, which we'll talk about later. But the random initialization actually may give you different cluster configurations depending on how you started. So that's another disadvantage. All right, so random initializations can lead to different clusters. And I'll give a graphical example of that later, and a way to combat this, cluster configurations. But yeah, I'll talk about how we can combat this later. Okay? Each time k-means is run. Okay? This is also what's known as local optima, and I'll give you some insight on what that means later. Okay? So this is the third problem, as we just talked about recently. If we have data that's highly overlapping, if you have, let's say one cluster has a bunch of data that is overlapping with another cluster, so if you try to run k-means, it won't be able to distinguish the 2 clusters. It'll just consider them as all one cluster, which is quite bad. All right? So if there are 2 clusters with highly overlapping data, k-means can't resolve that there are 2 clusters. So that's another disadvantage. Okay? Yeah, the disadvantages unfortunately keep on coming. So if you decide to take your data and apply some sort of transformation to it, whether you want to normalize the inputs or apply some sort of nonlinear transformation, if you run k-means on a nonlinear transformation of your data, the clustering configurations will also be different, because what you're doing is the Euclidean distance is the measure. So if you apply some nonlinear transformation, the Euclidean distance may not have the same meaning in this new domain. So that's why you may get different clustering configurations if you transform your data into some other space that is nonlinear. Okay, so if we apply nonlinear transformations to the data, it will give different results. And last but not least, I didn't talk about noise. So if you introduce the slightest bit of noise in your data, then k-means will also give you different results, because k-means is actually very sensitive to noise, because what you're doing is you're finding distances between clusters, right? So if you took, let's say, one cluster and you introduced a lot of noise to it, and then what happens is if you run the k-means algorithm with the points before the introduction of the noise, and it may not be close to a particular centroid, but if you introduce a lot of noise, then it might be close to another centroid than one is assigned to. So the cluster assignments may also be different if there's a lot of noise in your data. So sensitive to noise and outliers. So that sucks too. Okay, but anyway. But besides, even if that's the case, then it's quite a useful algorithm to know. It's one of the simplest to start off with unsupervised learning. So let me just finish our talk. Let me just finish this part of the lecture with a very graphical example, and then we'll take a break. Okay, so I pulled this example from Andrew Ng's slides, which is actually a very nice set of slides to show a graphical example. Okay, so what we're going to do is we're going to assume that we have two features, and these are the examples that we have. So, example, these are two features, right? And we don't know, so there's two features and there's a bunch of examples. And what we're going to do is we're going to have each label assigned to different colors. So the first label for the first the label for the first set of groups, the first set of points, for cluster number 1, is going to be red, and the second group, sorry, this is I, and then the second group will be assigned blue. Okay, so any points that belong to cluster number 1 will be red. Any points belonging to cluster number 2 will be blue. Okay, so that's what we're going to do. So this is the data that we have so far. And what we're going to do is we're going to try to run k-means on this to be able to find two different clusters of points. We can clearly see that there's two, but how do you tell a computer to do that? Right, so the first thing you have to do is you have to do some initializations. So this is the first thing we're going to do is the initialization. What we're going to do here is we're going to choose random points. We're not going to randomly choose examples just for illustration. So let's see here. Okay, so this is the initialization step. Okay, this is the initialization step. So what we're going to do is we're going to choose two random locations. Okay, for the cluster centroid. So we're going to initialize the cluster centroids to be these two guys here. So this is mu1 and this is mu2. So these are the initialized points. We usually choose training examples, but just to show you how flexible this algorithm is, we're just going to choose two random locations. Okay? So the first step, what you have to do here is you have to cycle through every single example and figure out which example is closest to which centroid. And whichever gives you the smallest distance, you assign the label of that example to be of that centroid. Okay? So this is the cluster assignment step. Okay? Initialization, and then we're going to do the first iteration. So this is the first iteration, iteration number 1. So this is the cluster assignment step. Okay. Okay, so if you take a look here, so all these points that are defined in red are the closest to this centroid in comparison to the blue. So for example, if you took a look at this example, you've calculated the distance between this centroid and this centroid. This is the one that is smaller. So what you do is you assign that point to be labeled 1 because it's closest to the centroid. Or if you take a look at this particular example, you calculate the distance between this centroid and that centroid, and you see that this one is smaller, right? So you're going to cycle through every single one of these points and find the distance between that point to all the centroids that you have, and then you choose the label that gives you the smallest distance to that particular centroid that is representative of that cluster. Okay? So each of these are assigned to cluster 1. Okay? And each of these guys are assigned to cluster 2. Okay? I'm almost done. I've only got like a few more pictures here. So let me just write some stuff down. So assign each example the label CI where not CI, denoting whichever centroid, which is U1 or U2, or mu1 or U2, it is closest to. Okay? So all these examples on the left belong to cluster 1 because they're closest to that centroid, and all the examples on the right belong to cluster 2 because they're the closest to that. So that's the cluster assignment step. And now what you have to do is you have to take every single example in each centroid and average them all together. So you're going to take all the X1 features, so this is X1 and this is X2. You're going to take all the X1 features that belong to cluster 1, average it, take all the X2 features, average it, and create a new centroid. Okay? So this is the movement step. Okay, this is still iteration 1. Okay, so this was the centroid before. Okay, and when we perform the average, we're moving here. This is where it moves. So this is the centroid after. Okay, let's see here. Right, this one was before, and this one was after. So it moves this way. Okay, so let's see here. So just as a quick notation here, so if you wanted to find the jth feature of a particular cluster, right, all you have to do is just, actually no, let me just do this here. So this guy here, if you want to find the update for each, all you have to do is just sum over every example that belongs to cluster 1. And just, oopsie. Sorry, let me call this I. Okay, so you're just averaging every example, that particular feature. Let me just do it again. This guy here. And this is 1, sorry. This is 2. Just want to be clear. Okay, so you're moving in that direction, and that completes the first iteration. Oopsie, I did that one already, sorry. I have to keep track of the numbers, so this is 5 now. Sorry, 4B. Okay, so iteration 1 complete. Sorry, I'm almost done. I'm overdue for a break here. I just have to show 2 more. So this is the next, so this is what it is after. And now what you're going to do is you have this configuration, you rerun the algorithm. So for each of these examples, figure out which examples are closest to each centroid and redo the label step. So this is the next iteration. 5. All right, so this is iteration 2. So this is the assignment step. Okay, now take a look here. You'll see that these labels here, the 5 examples here, and these examples over here, they change in assignment. So these guys change, right? As well as these guys changing here. Because these points are now closer to the red centroid, and these blue points are now closer to the blue centroid. Okay? So they actually change. So these are closer to the first one, and these are closer to the second one. Okay, so those labels have changed. And then you compute the update step. Very simple. Okay, so this is the update step. Okay, so what's happening now is this guy moves closer here, and this guy moves closer here. So this is the first one before, and this is after, and this is the same. So this is before and after. Okay, whoopsie. This one here was before, and this is after. Okay, so you do that, and then when you move that, then you complete it. Okay, so then, let's see here. Here. Okay, so this is complete here, so iteration 2 complete. And then you repeat the process all over again. So I'm just going to show you the last 2, and then we'll take a break. Okay, so this is the last 2, so we have 6, 7. Okay, so this is the assignment step. Okay, so if you take a look between them, you'll notice that these 2 points, these red points, and these blue points have changed because the cluster has moved. So these points have changed and these points have changed. Okay, and then when you compute the centroid, the update step, you'll notice that these centroids don't move anymore. So this is the update step. Okay. Well, once you update it, so once the memberships have changed, you move in this direction, right? And then finally, the last iteration will show you that it doesn't do it anymore. Okay, and that's it. All right, so if you try to do this again, so this is, this is the final stage. So you see here that once we move into the position, if we try to calculate it again, they don't move, and that's when you stop. Okay? All right, so we're going to take a break here. We'll come back, and then we'll talk a little bit more about k-means, and then we're going to get onto dimensionality reduction. Fun topic.